Swayam Prabha. Digital India. Educated India.
So, welcome to the 19th lecture of the NPTEL series on cryogenic engineering. Just to take a glance at what we learned in the last lecture, this topic is what we are talking about is basically gas separation. And during the last lecture, we found that synthetic membranes, adsorption, absorption and distillation are some of the common techniques of gas separation. We touched briefly to understand how do they function, what is the basic fundamental understanding regarding use of such processes for gas separation. We also found that mixing of two different gases is an irreversible process because unmixing or separation requires one work input. This is a common knowledge. We also calculated the ideal work requirement per mole of mixture to separate a mixture with n constituents, and that is given by minus Wi upon Nm, that is work of separation of gas per mole of mixture is equal to RTM sigma j is equal to 1 to n Yj log 1 upon Yj, where Yj is nothing but the mole fraction of the jth component. So, one can have 2 components, 3 components, 4 components, and accordingly the sigma terms will be Y1 log 1 upon Y1 plus Y2 log 1 upon Y2 plus Y3 log 1 upon Y3 etc. And the summation of that will give this sigma term. And this is the work of separation of these n constituents, maybe 2 or 3 or 4 per mole of mixture. With this background, let us find out what we are going to study in this lecture. Continuing with gas separation, let us keep studying ideal gas separation system, and what we will have here today is more tutorial based study. So, when we do some tutorials, we will understand the fundamentals of using this formulae, how to use those formulae and what the different variables and how we conduct parametric study using the tutorial. So, what is the effect of temperature? What is the effect of different mole fractions of gases? What happens we have got only 2 components or 3 components of gases? Let us try to study those parameters with the help of these tutorials. Let us go with a 3 gas mixture also, because the moment we go for higher gas components, the study can become more and more complicated to understand, and therefore, we will have one more tutorial having 3 gas mixtures. In general, the composition of any mixture can be specified in 3 different ways. They are volume percentage, weight percentage and mole fraction. This is again a common knowledge. I just want to touch upon these fundamentals because this is what we will be using in the tutorials etc. And this is very important and fundamental to all the calculations which we will be doing. So, a composition of any mixture can be given in volume percentage, or volume composition could be given, that volume of gas A, volume of gas B, volume of gas C in a mixture of A, B, C. Or we can have composition based on weights, that means how many grams of gas A, gas B or gas C will be given, or it could be a mole fraction, that means 80% or 20% molar fractions of gas A or gas B or gas C is given. So, these are the possible ways in which a composition of a mixture could be given, and accordingly we will have to do first important calculations and then convert or use mixture rules. In most of the gas separation problems, the correlations are based on mole fractions. So, if the fraction is given in mole fraction, absolutely all right. However, if they are given in weight percentage or weight composition or volume percentage, we will have to first convert this composition from volume weight to mole fraction and then utilize the mixture rules and things like that. So, first we will like to understand what these mole fractions are all about. Hence, all percentage have to be ultimately expressed in mole fractions. So, let us take a help of this tutorial 1, wherein we understand how do we convert the weight fraction into mole fraction or volume fraction into weight fraction etc. So, let us see the problem. Consider a mixture of gas A and gas B with a composition of 60% and 40% respectively by weight. So, first problem is basically referring the composition by weight in a ratio of 60 to 40% for gas A and gas B respectively. Determine the mole fraction of gas A and gas B if the temperature and the pressure of the mixtures are 300 Kelvin and 1.013 bar respectively. Given that the molecular weight of gas A and gas B are 28 grams per mole and 32 gram per mole respectively. So, the molecular weights are given over here. The second part of the problem says calculate the mole fractions in the above percentage, that is 60-40 percentage, are given in volume basis. So, first problem is basically the composition which is given in a weight composition, and the second one is given on a volumetric basis. So, ultimately we would like to convert these fractions into molar fractions of gas A and gas B respectively. So, what do we do? So, working pressure is 1 atmosphere, temperature is 300 Kelvin. The mixture compositions in the case 1 60% A and 40% B by weight of A and B per weight of mixture, or 60% A plus 40% B by volumetric basis. For above mixtures, calculate Ya and Yb. What are Ya and Yb? They are the molar fractions of A and B. That is what the problem statement is. So, first let us take the 60% A and 40% B by on weight basis. So, let us say this is a mixture where A and B are in a ratio of 60 to 40 by weight. Let the mass of the mixture be x grams, all right. Then the mass of gas A in the mixture is 0.6 x grams. This is clear. The total mixture gram is x, and therefore 0.6 x constitute the mass of gas A. The number of moles in gas A therefore will be the total mass of gas A divided by molecular weight. So, Na is equal to 0.6 x upon 28, 28 nothing but the molecular weight in grams of gas A. Similarly, the number of moles of gas B will be Nb is equal to 0.4 x upon 32. 0.4 x is nothing but 40% by weight of the mixture. So, 0.4 x upon 32 will be the molar fraction or number of moles of gas B. So, the total moles in the mixture are Na plus Nb is equal to N total is equal to 0.6 x upon 28 plus 0.4 x upon 32. It's clear, this is N total. So, if I want to find the molar fraction of gas A now, what is the definition of molar fraction? Ya is equal to Na upon N total. That means number of moles A in a mixture divided by total number of moles. And if we write Na in terms of what we have written earlier, we got 0.6 x upon 28, which is nothing but Na divided by N total, which is what 0.6 x plus 28 plus 0.4 x upon 32. If we take out x from all these things, what we get Ya is equal to 0.631. That means the molar fraction of A is 63.1%. However, the weight percentage is 60% here. All right. That means the molar fraction is different than that given by the on the weight basis. If we come to gas B now, we have got a Yb is equal to Nb upon N total, and write the value of Nb on the numerator now here and the total number of moles in the denominator. Again, the answer will be now Yb is equal to 0.369, that is 36.9% is the molar fraction of Yb. So, the 60% by weight and 40% by weight B get reduced to 0.631 molar fraction of Ya and 0.369 molar fraction of Yb. And this is what we will be using further for the calculations of work of separation. So, Ya and Yb are computed from a weight percentage, from a weight composition. Okay. Now, let us see the second case when the volumetric composition is given for A and B. So, we got a 60% A and 40% B by volume basis. So, let us say this is 60% A basically, okay, which is it is going to take 0.6 times the total volume. The amount of volume it is occupied by A is going to be 0.6 times V total, where V total is the volume occupied when the two gases come together. Okay. So, plus we have got a second gas which is gas B, and it occupies 0.4 times Vt, that means 40% of total volume, which is 0.4 T, and when they combine together what you get is a Vt. So, what we know here is gas A occupies 0.6 Vt, gas B occupies 0.4 Vt, where Vt is the total volume when the gases are mixed together. So, what do we calculate? Let us calculate number of moles of gas A, number of moles of gas B, and total number of moles will be number of moles of gas A plus number of mole of gas B. So, let the moles of gas A be Na, and using ideal gas law, what we know is Na is equal to PV upon RT, Na is equal to P into 0.6 Vt upon RT. Similarly, the moles of gas B will be Nb, which is equal to P into 0.4 Vt upon RT. So, we got a Na and Nb, number of moles of A and number of moles of B calculated based on their respective volumes occupied. So, the total number of moles will be N total, which is equal to Na plus Nb, and if we put those values, this is what the expression comes for N total. Going further, now let us calculate the molar fraction of gas A, which is given by Na upon N total, right. This is clear to us. So, Na upon N total is equal to whatever Na we have calculated just now divided by N total. So, if I go on, I can just cancel PVT upon RT from all these three entities, giving me Y is equal to 0.6. That means 0.6 was nothing but the volumetric composition of gas A, and the molar composition of also is coming to be 0.6. Similarly, if I do for gas B, again I calculated the molar fraction of gas B, which is Nb upon N total. I put respective values of Nb and N total. Again I do cancel the common term, and I get Yb is equal to 0.4. So, the molar fraction is 0.6 for A and 0.4 for B, which is same as what it is given in a volumetric composition of a mixture of gas A and B, which means that the molar fraction remains essentially remains the same as volumetric composition, but the molar fraction are not same when the composition is given on weight basis. This is essentially what we understand from this tutorial 1. So, what we say is volume fraction is equal to mole fraction. So, ultimately now we have understood how to calculate the molar fractions whenever the composition is given based on weight or based on volume. If it is directly given in terms of molar fraction, fine, one can immediately start calculating the work of separation of this gas mixture. But if it is not, then we will have to convert them first to the molar fraction as done in this particular tutorial. Okay, now let us come to the calculation of work of separation. Let us see the ideal separation system. The ideal work of separation per mole of mixture, let us say in a mixture of gas A and gas B, is given by this formula. This is what we had derived last time. Wim upon Nm is equal to Rtm into Ya log 1 upon Ya plus Yb log 1 upon Yb, where Ya and Yb are nothing but molar fractions of gas A and gas B respectively. On the similar line, if the mixture is composed of three different gases, gas A, gas B and gas C, the ideal work of separation per mole of gas is given by this formula, where Ya, Yb, Yc are the mole fractions of A, B and C respectively. This is clear. Now, let us see the tutorial where we understand all these respective values, where we will calculate the work of separation and we will understand the different nomenclature used in work of separation. So, the tutorial 2 is aiming towards understanding this the ideal work of separation of mixture. So, the problem statement let us read. Determine the Wim by Nm, that is work of separation of mixture per mole of mixture, Wim by Nn2, Wim by NO2. The mixture is given as a mixture of N2 and O2, nitrogen and oxygen, for the separation of a mixture of gases consisting of 80% nitrogen and 20% oxygen by mole fractions. That means Ya and Yb have already been given. The mixture is at 300 K and the pressure of 1.013 bar, 1 atmosphere. The molecular weights of nitrogen and oxygen are 28 and 32 grams per mole respectively. For the above statement or the above problem, also calculate the ideal work requirement for the unit mass of nitrogen and oxygen respectively. Okay. So, the work of separation, and here we want to calculate per unit mass of gas also. This was per unit mole of nitrogen and oxygen. The problem statement also calls that calculate the work requirement per unit mass of nitrogen and oxygen respectively. So, what is the data given, which is working pressure 1 atmosphere, temperature 300 Kelvin, mixture 80% nitrogen and 20% oxygen by mole fraction. So, Ya is 0.8, Yb is 0.2. Now, the nomenclature that we are going to follow from this lecture onwards is to understand this, and these are the terms which normally will be used. So, what is Wim by Nm, that is work of separation of mixture per mole of mixture. So, when I say Wim, this is work of separation of mixture. When I say Nm, that is a mole of mixture. So, this is nothing but work of separation of mixture per mole of mixture. Now, this can also be interpreted in terms of mole of oxygen or mole of nitrogen, which constitutes one of the parts of the mixture or one of the gases of the mixture. So, I can ask for Wim by NO2, which is work of separation of mixture per unit mole of oxygen, work of separation of mixture per unit mole of nitrogen. When N get replaced by M, we can say it is per gram of oxygen or per gram of nitrogen. So, the mass comes into picture. So, Wim by MO2 is nothing but work of separation of mixture per mass oxygen, work of separation of mixture per mass of nitrogen. So, there are different terms here, per mole of mixture, per mole of oxygen, per mole of nitrogen, or per gram of nitrogen, per mass of oxygen, per mass of nitrogen. So, depending on the problem statement, one has to calculate all these things and one has to present the results. Alright, so ideal work per mole of mixture, which is Wim upon Nm, and this is standard formula. So, basically now put the values. So, we know R is a universal gas constant 8.314, Tm is equal to 300 Kelvin, Y is 0.8, Yb is 0.2. Putting this value, Wim upon Nm is equal to this formula 0.8 log 1 by 0.8, 0.2 log 1 by 0.2 into RTM, and this is giving you 1248.1 joule per mole. This is work of separation of mixture per mole of mixture. Now, I would like to write the same work in terms of mole of nitrogen. So, now I will be using ideal work per mole of nitrogen. How do I calculate that? So, for that I will use a formula. How can I write that? Wim upon Nn2, which is what is required. Work of mixture, work of separation of mixture per mole of nitrogen can also be written as work of separation of mixture per mole of mixture into moles of mixture divided by moles of nitrogen. The moles of mixture Nm and Nm will get cancelled, and ultimately what you get is a work of separation of mixture per mole of nitrogen. Alright. So, this is what we get from this, and if I, what is Nm upon Nn2? It is nothing but mole fraction of nitrogen. If I put Nm down, Nn2 divided by Nm is nothing but Yn2. Nm upon Nn2 is nothing but 1 upon Yn2. So, if I replace that, I will get Wim upon Nn2 is equal to work of separation of mixture per mole of mixture divided by Yn2. So, if I know Yn2, I can calculate the work of separation of mixture per mole of nitrogen by this formula. So, what is Wim upon Nm, which we have just calculated, which is 1248.1, Yn2 is 0.8, that is mole fraction of nitrogen in a mixture. So, Wim upon Nn2, which is work of separation per mole of nitrogen, is 1248.1 divided by 0.8. If I put this, I get 1560.1 joules per mole of nitrogen. This is my work of separation per mole of nitrogen. Now, I can do the same thing per mole of oxygen also. So, my next calculations are ideal work requirement per mole of oxygen. Going by the same study now, my work of mixture per mole of oxygen will be Wim upon Nm divided by molar fraction of oxygen, which is 0.2. So, this is 6240.5 joules per mole of oxygen. And similarly, now I can calculate ideal work per mass of nitrogen. I just convert the moles of nitrogen into the mass. So, Wim upon Mn2 is equal to Wim upon Nn2 into Nn2 upon Mn2. What is mass of nitrogen per mole of nitrogen? Is it molecular weight? What is Mn2 upon Nn2? Nothing but molecular weight. Nn2 upon Mn2 is nothing but 1 upon molecular weight. Mn2 is a mass of nitrogen per mole here. So, I can put the molecular weight. Putting the values over here in this formula, I will get Wim upon Mn2 is equal to 1560.1 upon 28. So, 55.71 joule per gram of nitrogen is the ideal work of separation per mass of nitrogen, and same thing I can do for mass of oxygen by just putting the molecular weight of oxygen as 32 in this, and you get 195.01 joule per gram of oxygen. So, tabulating the results, I get work of separation per mole of mixture, which is 1248, work of separation per mole of nitrogen, which is 1560, and work of separation per mole of oxygen 6240.5. If I go further, going from moles of nitrogen to mass of nitrogen, I can get Wim upon Mn2, that is work of separation per mass of nitrogen, as this work of separation per mass of oxygen, which is this. And always you can find that Wim upon Nm is going to be less than any other component. This particular value is going to be less because Nm is always more than Nn2 or NO2. Nm, which comes in the denominator, is always going to be more than Nn2 and NO2, or Nn2 and NO2 is always going to be less than Nm, and that is why these two values will always be more than Wim by Nm by simple algebra basically. Now, if I go for the parametric study, I want to understand what is the effect of molar composition, what is the effect of temperature, etc. I can understand by carrying out different parametric studies. So, as mentioned earlier, the ideal work of separation for a gas mixture gas A and gas B is given by this formula, which we know about. Since Ya and Yb are the mole fraction of gas A and gas B respectively, the following condition is always true at all the time. Ya plus Yb is equal to 1, and therefore, Yb can be always be 1 minus Ya. If I put these two values, and this is possible when I am talking about two gas mixtures, gas A and gas B, substituting these values, what you get is this Ya log 1 by Ya plus 1 minus Ya log 1 minus Ya. Need not be written Yb every time, alright. So, I can understand from these figures that it is clear that the ideal work of separation for a mixture is depends on mole fraction, that is Ya and Yb from gas A and gas B respectively. Also, the work requirement decreases with the decrease in temperature. You can see the Tm value over here. So, depending on what is my quantity of Ya and Yb, the ideal work of separation will vary. Also, depending on what the temperature of separation is, the Wim by Nm value will vary. The effect of Ya and separation temperature on the ideal work requirement is studied in a greater detail in the next tutorial. So, let us study what is the effect of Ya and Yb, and also what is the effect of Tm on the work of separation. So, for which we have taken a separate tutorial again to understand this dependency of these parameters, and let us study how Ya and Yb and temperature of separation change the work of separation for different gases. So, the tutorial 3 aims at this, and the problem statements are: consider mixture of gas A and gas B with following compositions in mole fractions. So, we got a different compositions, composition 1, 2, 3 and 4 with 30% A, 70% B, 50% A. So, we go on increasing the value of A from 30 to 80, and we go on decreasing corresponding the values of mixture composition value of B, 70, 50, 40 and 20, making it 100% all the time. So, determine Wim by Nm, which is work of separation of mixture per mole of mixture, Wim by Na, we know what it is now, Wim by Nb for the separation of this mixture, given that the mixture is at 300 Kelvin and 200 Kelvin. So, I want to have two cases. One is the mixture separation is at 300 Kelvin or mixture separation is at 200 Kelvin. The mixture pressure is 1.013 bar. So, working pressure is 1 atmosphere, temperature 300 Kelvin and 200 Kelvin. The mixture compositions are case 1, case 2, case 3, case 4. And for above mixtures, calculate Wim by Nm, which is work of separation of mixture per mole of mixture, Wim by Na, work of separation of mixture per mole of gas A, Wim by Nb, which is work of separation of mixture per mole of gas B. The two separation temperatures under study are 300 Kelvin and 200 Kelvin. In this tutorial, the Wim by Nm, Wim by Na, Wim by Nb are calculated only at 300 Kelvin and for mixture 3 only. That means, all the calculations are shown only for case 3 and at 300 Kelvin, while all other calculations pertaining to 200 Kelvin and other mixtures are left as an exercise to the students. The data is plotted graphically in further slides. So, let us first calculate ideal work requirement per mole of mixture for case 3. So, this is our formula, which is very well known now. The data is given, and for case 3, Ya is 0.6, that is 60% of A and 40% of B, 0.6 and 0.4. So, calculate Wim by Nm, put this 0.6, 1 by 0.6, 0.4 log 1 by 0.4. The answer is 1678.6 joule per mole of mixture. So, work of separation is this quantity for 60-40 cases. Ideal work per mole of A, which is Wim upon Na is equal to Wim by Nm into 1 by Ya, just divided by the mole fraction. So, what we get is 1678.6 divided by 0.6, and we get 2797.6 joule per mole of A. Similar thing I will do to calculate ideal work per mole of B now. Just divide it by the mole fraction of B and we will get the answer for this, which is 4196.5 joules per mole of B. So, we have calculated work of separation per mole of mixture, work of separation per mole of gas A and work of separation per mole of gas B for a mixture which had 60% A and 40% B on a molar fraction basis. Extending the calculation for all other mixtures at 300 Kelvin, we have got the following table. So, this calculation was shown in detail. Now, let us do it for all the mixtures case 1, case 2, case 3, case 4, and this is my table. So, first is we are doing all this studied at 300 Kelvin and first case is 30% A and 70% B, where WIM by Nm, work of separation of mixture per mole of mixture is 1523, WIM by Na is 5078, WIM by Nb is 2176. And if I go for increasing the value of A, correspondingly decreasing the value of B, you can see that the work of separation of mixture has increased first and then starts decreasing. So, 1500, 1700, then 1600 and 1200 and odd kind of work you can see over here. And as the A component increases, what you can see that the work of separation per mole of gas A is decreasing, because the molar composition for A is increasing. And similar thing, as the molar composition of B is decreasing, we can see that WIM by Nb is increasing in this case. We can study and understand this in better details when we go for a graphical understanding. For any given mixture, applying the same analogy as WIM by Nm is always less as compared to WIM by Na or WIM by Na. So, one can see that 1523 is less than 5078 and less than 2176, because Nm is equal to Na plus Nb. So, Nm value in the denominator is always going to be more as compared to Na and Nb, and that is why work of separation per mole of mixture is always going to be less than work of separation per mole of gas A or per mole of gas B. This is what we saw earlier also. Similarly, the calculations for all other mixtures at 200 Kelvin temperatures, the results are as tabulated below. So, we had done calculations at 300 Kelvin, which is the separation temperature, as well as we have carried out all the studies at 200 Kelvin also. So, this is the table now gives for 200 Kelvin WIM upon Nm, WIM upon Na, WIM upon Nb, and these are the mixture studies case 1, case 2, case 3, case 4, and again you can find similar trend as the value of separation per mole of mixture goes first increasing and then start decreasing down. You can see the similar trend as what you saw earlier for work of separation per mole of gas A, which is decreasing as the composition of A increases in a mixture. Similarly, you can find the work of separation per mole of gas B increases as the molar percentage of B decreases in a given mixture. Now, if I want to study the same thing in a graphical form, just to have a better understanding, I have plotted here work of separation of mixture per mole of mixture versus Ya, that is molar fraction of gas A. So, gas A molar fraction is increasing in the right side, and on this pattern, on this y axis, what you see is work of separation per mole of mixture. The plot of WIM upon Nm versus Ya for 300 Kelvin and 200 Kelvin are shown. What are these cases? Case 1, case 2, case 3, case 4, and let us see all these 4 points. So, we point 1523 other things, and if we join, this is a 300 Kelvin curve. That means, you can see that the work of separation of this mixture per mole of mixture touches maxima somewhere over here and comes down. And if I do the same thing for 200 Kelvin and point case 1, case 2, case 3, case 4 points and connect them together, I get a similar trend. What you can see from here, that this curve is at a lower level as compared to 300 Kelvin, meaning which directly that the work of separation requirement is less for 200 Kelvin than at 300 Kelvin, and this is what our first conclusion should be. It is clear that work of separation per mole of mixture decreases with the decrease in separation temperature, and this is clear from the formula itself. Now, what is to be understood is also for a given mixture and temperature, the Wm upon Nm crosses a maxima, which is what you can see, the maximum here, the maximum here. And what is most important to understand is this maxima occurs when the mole fractions of gas A and gas B are equal. That means the maximum happening at 0.5. When Ya is equal to 0.5, correspondingly Yb also is equal to 0.5. So, Ya is equal to Yb is equal to 0.5, and the work of separation is maximum when Ya is equal to Yb is equal to 0.5. So, the maximum occurs when the mole fractions of gas A and gas B are equal, and this is mathematically correct. If you see the formula, you can see that when Ya is equal to Yb, this Wm upon Nm will be maximum. In case of 3 gas mixture, suppose instead of going for gas A and gas B, if I go for gas A and gas B and gas C, the horizontal position of maximum occurs when Ya is equal to Yb is equal to Yc is equal to 0.33. So, I will get maximum now when all the 3 gases are present as 33.33%, actually they are equal percentage basically. So, this position of the maximum is independent of separation temperature. As you can see, maximum occurring at 300 Kelvin and at 200 Kelvin are at the same location. So, basically the position of maxima is independent of what is the temperature of separation is. Yeah, and it completely depends on when Ya is equal to Yb is equal to Yc in 3 gas mixture. Now, if I want to plot, this is what we plotted first of work of separation per mole of mixture. Now, instead of that, I am now computing work of separation of gas per mole of A, gas A against Ya. So, Wm upon Na on y axis and Ya or a molar fraction of gas A on the x axis. The plot of Wm upon Na versus Ya for 300 Kelvin and 200 Kelvin are as shown here. So, what are my cases? Case 1, case 2, case 3, case 4. And if I join them, what you can see that as the value of Ya increases, the work of separation of the mixture per mole of gas A decreases, and this is for 300 Kelvin. If I do it 200 Kelvin, I find the work of separation has decreased per mole of gas A at 200 Kelvin. So, the conclusions that can be drawn here are similar to what we saw earlier. It is clear that Wm upon Na, that is work of separation per mole of A, decreases with the decrease in separation temperature. Also, for a given mixture and temperature, there is a steep decrease in Wm upon Na with the increase in the concentration of a particular ingredient. That is, as you go on increasing the Ya value, or as you go on increasing the concentration of gas A in a mixture, Wm upon Na is going to be decreasing, because naturally if you see mathematically, the denominator goes on increasing, and therefore Wm upon Na will start decreasing as you go with the increase in the value of Ya. Similar thing will happen even if the temperature is lowered from 300 Kelvin to 200 Kelvin. Alright. So, what we saw from all this tutorial is what happens to the work of separation. First of all, we understood what are these different nomenclature: Wm upon Nm, Wm upon Na, Wm upon Ma, work of separation of mixture per mole of gas, work of separation per mole of A, work of separation per mass of A. These are 3 different quantities. Also, we understood that the work of separation passes through maxima, work of separation depends on the separation temperature, and now we will go for a different study. Going ahead from what we have learned, now for a mixture with 2 ingredients, the separation results in 2 separate components. This was a simple case. You got a gas A and gas B, separate out gas A and gas B. But we can have we have got a mixture wherein we can have 3 components: gas A, gas B and gas C. So, but for a mixture with 3 ingredients, say gas A, gas B and gas C, following cases of separation are possible. What are these cases? All 3 gases are separated from each other. That means, after separation I get gas A, gas B and gas C. The second case is only one gas is separated, leaving other 2 gases mixed. That means, I am not interested in any other gases but gas A, and therefore, from a mixture of A, B and C, I would like to take only gas A out and would not bother to separate B and C. Let them remain combined. So, what I am going to separate out from A, B, C is only A, and the other lot will be B plus C. So, work of separation of gas A, gas B and gas C, that means work of separation of the entire mixture is one case, which is what is given by the first case, while I could be interested only gas A or gas B or gas C. That means, let us say I am interested in gas C. So, my separation problem will be now separate gas C from A and B. So, work of separation of separating gas C from A and B will be different than separating all three gases. Do you understand the difference? There is a difference between separating A, B and C from each other or separating only one of the gases from the mixture of other two gases. Okay? And this is what I am interested in. I want to calculate the amount of what is the work input required just taking out gas A from a mixture of gas A, B, C, or I want to calculate the amount of work to be done in order to separate A, B and C from each other. That means, I need A, B and C, all three different gases to be separated in that case. The following tutorial is taken up to have a better understanding of this concept, because this concept is a very different now, and let us understand it from using this tutorial, and so that we can get some quantitative feeling also at the same time we can understand the qualitative approach also. So, the tutorial 4 basically is solved to understand the mixture of three different gases and also conceptual understanding of separation of one of the components from this mixture of three gases or separating all these three components from each other can be understood from this tutorial 4. So, what is the problem statement reads? The problem statement is, consider air as a mixture of 78% nitrogen, 21% oxygen and 1% argon by mole fraction. Determine the work requirement per unit mole of argon when all the three gases are separated and only when argon is separated. That means, first case is what is work of separation per unit mole of argon, and second thing is what is the work of separation when only argon is separated from this mixture of three gases. The mixture is at 300 Kelvin and at a pressure of 1.013 bar. The second part of the problem also reads like this. For the above problem, calculate the above parameters for the case of oxygen. So, instead of argon, have oxygen. All right. Comment on the results. So, important is comment on the results and explain the results basically. So, what are the parameters given? Working pressure is given, temperature is given, and the mixture composition on molar basis also is given. So, what are the molar basis? 78% nitrogen, 21% oxygen, 1% argon. So, 0.78, 0.21 and 0.01. That is what our molar fraction of the mixture nitrogen, oxygen and argon is. What is to be calculated is all these parameters. So, what are all these parameters? Let us read one by one. So, Wim by Nm is work of separation of mixture per mole of mixture. Then we go to Wm upon NAR, which is work of separation of mixture per mole of argon. Then work of separation of argon per mole of mixture. Work of separation of oxygen per mole of mixture. Work of separation of mixture per mole of argon. Work of separation of mixture per mole of oxygen. Then work of separation of argon per mole of argon. Work of separation of oxygen per mole of oxygen. So, all of them are different quantities. So, here in the first part or the first column, the separation is done per mole of mixture. All right. So, Wm upon Nm, work of separation per mole of mixture, work of separation of argon per mole of mixture, work of separation of oxygen per mole of mixture. On the right side, I need the values with respect to one of the gases, which is argon and oxygen. So, here I say work of separation of mixture per mole of argon. Here I say work of separation of mixture per mole of oxygen. Now, here I want to convert this quantity. Instead of per mole of mixture, I want per mole of argon. Work of separation of argon per mole of argon and work of separation of oxygen per mole of oxygen. This concept should be absolutely clear. What is asked in a problem and how do we get those values basically? This should be absolutely clear. All right. So, please get used to this nomenclature, and this is what a new nomenclature, and it is a very important to understand this nomenclature. So, let us calculate first Wim by Nm, which is work of separation of mixture per mole of mixture, and you got a formula here. So, RTM, work of mixture consists of three gases, argon, oxygen and nitrogen. So, we got A, B and C terms. So, we got a YAR log 1 upon YAR, YO2 log 1 upon YO2, Yn2 log 1 upon Yn2. All right. So, we got a terms for gas A, gas B and gas C, which is sigma term basically. So, putting those values, what was Yn2 0.78, YO2 0.21, YAR 0.01. Put those values in equation you get work of separation of mixture per mole of mixture is equal to 8.314 into 300, 0.78 log 1 upon 700, 0.21 log 1 upon 0.21 plus 0.01 log 1 upon 0.01. This is equal to 1415.6 joules per mole of mixture. So, work of separation per mole of mixture is given by this. That means, all the three components are separated and the work is represented per mole of mixture. Now, I want to represent the same thing as per mole of argon. So, work of separation of mixture per mole of argon is divide this by argon, molar fraction of argon, as we have seen earlier. So, which is 1415.6 divided by 0.01, and suddenly this value will be very high, because the molar fraction of argon is very small, 0.01. So, work of separation of mixture per mole of argon is going to be a huge quantity, 141560 joule per mole of argon, because the fraction, the molar fraction of argon is very small quantity, all right, and therefore, this division gives a very large number, a big number. Now, I want to calculate work of separation of mixture per mole of oxygen. So, what is the molar fraction of oxygen is 0.21. So, I divide this by 0.21 now, instead of 0.01 in earlier case, I divide by 0.21, and now I get work of separation of mixture per mole of oxygen as 6740.9 joule per mole of oxygen. And this is my work of separation per mole of oxygen. And now, I got a work of separation of argon per mole of mixture. This problem is different than what we have studied earlier. Earlier, we were separating only work of separation of mixture. Now, here I want to calculate only work of separation of argon from the given mixture. The formula is going to be different in this case, so be careful. So, what my formula will be now? Work of separation of argon per mole of mixture is equal to RTM. Now, my gas A is argon and my gas B is a mixture of other two gases, because I am not bothered about oxygen plus nitrogen now. I just want to take argon out from a mixture of argon plus oxygen plus nitrogen. So, my gas A is going to be argon and my gas B is going to be mixture of two gases, all right, oxygen plus nitrogen. So, formula is YAR log 1 upon YAR plus YO2 plus N2 log 1 upon molar fraction of oxygen plus nitrogen. This is a small mixture by itself, because of a mixture of A plus B plus C, I just want to take out A, that is it. I am not interested in separating B and C. So, B and C will always remain in a mixture form here. So, what is my YAR? YAR is 0.01 and YO2 plus N2 is 0.99, nitrogen plus oxygen, 0.78 plus 0.21, which is 0.99, all right. So, this is what YO2 plus N2 will figure here. So, putting these respective values over there, work of separation of argon per mole of mixture is equal to 8.314 into 300, 0.99 log 1 upon 0.99, which is this particular bracket, plus 0.01 log 1 upon 0.01, which is referring to the argon gas, and is equal to 139.6 joule per mole of argon, mole of mixture. This is what my work of separation per mole of mixture is given as. Now, I want to convert that and represent in terms of mole of argon only. So, my work of separation of argon per mole of argon is equal to, I know work of separation of argon per mole of mixture. So, I will just divide by molar fraction of argon basically. So, work of separation of argon per mole of argon is equal to 139.6 divided by 0.01, which is 13960 joule per mole of argon. Now, this is clear, we have done it several times now. So, the concept should be absolutely clear by now. Now, I am calculating work of separation of oxygen per mole of mixture. Again got instead of argon, now I am separating out only oxygen, and the other part will remain is now mixture of argon and nitrogen, all right. So, I got a YO2 log 1 upon YO2, I got a YAR plus N2 log 1 upon YAR plus N. So, what is the value of YO2? 0.21 molar fraction of oxygen, and Y nitrogen plus argon is 0.79, which is nitrogen plus argon, all right. So, putting those values over here, I will get these values, which is work of separation of oxygen per mole of mixture. And now, I can convert the same to understand what is my work of separation of oxygen per mole of oxygen. WiO2 divided by Nm is 1300 0.8. The molar fraction of oxygen is 0.21. So, WiO2 per mole of oxygen, work of separation of oxygen per mole of oxygen is equal to work of separation of oxygen per mole of mixture divided by YO2, that is molar fraction of oxygen, which is 1300.8 divided by 0.21, which is 6194.3 joules per mole of oxygen. This is my WiO2 per mole of oxygen. So, tabulating all the results together, what we can get is a combined look, work of separation at 300 Kelvin. So, work of separation per mole of mixture is 1415.6. Work of separation of argon from this mixture per mole of mixture is very small, 139.6, all right, argon being a very small quantity. Then work of separation of oxygen per mole of mixture is 1300.8. This is oxygen is going to be separated from the mixture per mole of mixture. Now, I can represent per mole of mixture as per mole of argon or per mole of oxygen. So, this is just a representation style. So, I can get now work of separation of mixture per mole of argon. So, divide this by a molar fraction of argon, which is this. And because the molar fraction of argon is very small, this quantity looks very big. And work of separation of mixture per mole of oxygen is given by this. Similarly, I can represent work of separation of argon per mole of mixture in terms of work of separation of argon per mole of argon also, which is what is given by this. Also extending, instead of having Nm, I can have NO2, it is work of separation of oxygen per mole of oxygen, which is 6194.3. So, eventually one may ask you, what is this value WiO2 by NO2, or it could be only WiO2 by Nm. So, what is important is what has been asked. It basically one can understand from work of separation of work of liquefaction per mass of gas which is compressed. If you remember my earlier topic, work of liquefaction per mole of gas which is liquefied. Similarly, here work of separation per mole of mixture or per mole of oxygen or argon or nitrogen or whatever. So, thus understand the problem statement and represent your work of separation per mole of mixture in terms of per mole of oxygen or argon or nitrogen for that matter. Coming to the summary, with all this understanding of work of separation of gas A, gas B and gas C, we have understood various nomenclature represented to calculate the work of separation of gas A or work of separation of gas B or work of separation of the entire mixture, and that could be terms as per molar basis on a mixture or per molar basis of oxygen or nitrogen or gas A or gas B or gas C. It could be anything, all right. So, in summary, in general, the composition of any mixture can be specified in three different ways. They are volumetric percentage, weight percentage and mole fractions. So, as you understood, what we ultimately want is mole fraction. So, suppose the problem has not been given into mole fraction or the composition has not been given on a molar basis, we can have convert the weight percentage, weight composition into molar composition, while we know that the volume composition is nothing but the molar composition itself. So, in that case we do not have to do any extra algebraic calculations. Work per mole of mixture is always less than work per mole of its constituents for any mixture. This was clear because we know that Nm is equal to Na plus Nb, where Na, A and B are the constituents of mixture. So, work per mole of mixture is going to be always less than work per mole of gas A or work per mole of gas B, because mole of gas A and gas B fraction is going to be less than 1, less than the moles of mixture basically. So, Wim by Nm is maximum when the percentage compositions of all its ingredients are equal, which we found that from the graphical representation, that when gas A is equal to gas B is equal to 0.5, we hit the maximum. The work of separation in that case is maximum. Similarly, for three components, when the gas A is equal to gas B is equal to gas 3 is equal to 0.33, then it will hit the maximum. The work of separation is going to be maximum in that case. So, this is just to understand the same thing. With the decrease in the percentage, work per mole of component increases. So, as the percentage composition of that particular component decreases, the work of separation, the work per mole of that component, that means work per mole of gas A will increase if the gas A is percentage is decreasing in that case. This is what we saw again graphically when we saw Wim by Na as a function of Ya. All right. With this background, an assignment has been given for a mixture of gas A, gas B and gas C. Percentage has been given, mole fractions. You determine the work requirement per unit mole of C when all the three gases are separated and only when C is separated. So, it is a similar kind of problem what we have just solved. The mixture is this and the pressure is given. For the above problem, calculate the above parameters for the case of B and comment on the results. So, this is a very important thing. Please do carry out these calculations. The answers are given over here. So, please check your answers after this and see that they are correct. Thank you very much.